Hey, good afternoon. I'm Micah, co-founder and CEO of Artificial Analysis, and I'm going to be talking a bit about AI benchmarking today. So, let's make sure that, everything working. Excellent, cool. So, for anyone who's not familiar, Artificial Analysis is an AI benchmarking company. We run a website at artificialanalysis.ai for developers and companies looking to use AI models to build applications. We benchmark models, infrastructure, and chips. We're testing intelligence, speed, cost, efficiency for all kinds of AI models. We started the website a bit over a couple of years ago now, because my co-founder and I were AI founders ourselves looking to build AI applications. And we're finding that no one was doing good enough independent benchmarking to give us the answers we wanted for building things. That's been our mission the whole way through. And what we're going to do today in this talk is have a look at some of our data, the trends that we're tracking, and what that means for everyone here today looking to build stuff with AI. So, to conclude some of the background stuff, as a company now, we work with most of the leading players across the AI stack. So that includes most of the labs building language models, the labs building image, video, and speech models, and then the companies doing infrastructure and chips that all this runs on. We're a team of about 20 based in San Francisco, but very nice to make the trip over to Paris for today. The content that's in this talk, a lot of it comes from our quarterly State of AI report. I put this up just for a little bit of context of some of the stuff that we publish. So we've got the free website. For our enterprise customers, we have some of the reports that are on the screen here today. And then we spend a lot of our time building data sets and tools for doing benchmarking, some of which we build for internal use and others that we're using with the labs that we work with and with our enterprise customers. Long and short is, if you've got tricky problems with AI benchmarking, whether it's about things that relate to the leaderboards and things that we publish now, or about custom problems that we don't currently solve, we're very open to a conversation. Okay. So, enough about us. What we're going to spend most of this talk doing is talking about stuff that's going on in AI. We're going to talk about some stuff about the current state of language models, some of the trends that we're tracking, and then a little bit of a deep dive into, call it some of the exciting stuff happening in Europe. This particular week to get to speak just after Mistral launched their models yesterday, depending on time zone, 2 days ago, I guess, actually in Europe time. It's kind of cool because we can do a little bit of a case study on some of the benchmarking and data stuff that we do at Artificial Analysis, looking at those Mistral models. Okay, that's basically the same thing I just said. So, this here is one of the charts that we always start with at Artificial Analysis, and you'll find it at the top of the website on the homepage. And it charts our intelligence index metric over time. The Artificial Analysis Intelligence Index is our single synthesis metric that takes together a whole bunch of the evals we run, a bunch of industry standard open source ones, some that we develop ourselves, and puts them into one nice simple number for us to look at how model intelligence has evolved over time. It's a pretty useful number. I would say probably the single most useful number if you want one number to know how smart models are, but I don't think any of you will be surprised that I'm going to tell you that taking a single number to know how smart AIs are does not tell you the whole story, and there's always more you want to look at for any kind of use case. That being said, this is a pretty interesting chart, and there's a lot that we can learn from it. So, we're starting back with the launch of GPT 3.5 on the far left-hand side of the screen. We can see that we've got this era of OpenAI dominance after GPT-4 comes out, where there was a scramble for a whole bunch of other companies to catch up. And then you can see in late 2024, the emergence of reasoning models, and they're causing a significant jump in the evals that we use to track intelligence here. And then you can see on the right-hand side, what's happened over the course of 2025 with fierce competition and much less of a gap between those leading labs that we're tracking here. We're going to come back to talking a bit about Mistral, so I won't dive into that now, but some specifics that I do want to call out here is that we've now got on the top right each of the 3 frontier labs pretty much neck and neck, and we'll look at another chart to see the current state of things, but with those dots up the top. And broadly, just a very competitive but still fast-moving set of benchmarks here. One thing that I think it's really helpful to see here when we zoom out is just how much has happened in the last 2.5 years. I think one of the moments this year that had mixed reception was when OpenAI launched GPT-5, and I think the reaction for a lot of people in the industry was, wow, like this does not feel hugely different to the things that I had been using just before it came out. What that misses is that where we are now is an enormous leap from 2.5 years ago, from 1 year ago. A year ago, on all of our agentic coding evals, none of the models were getting a whole lot done. And for those of us who use those, like you can feel that, right? That just over a year ago, coding agents really didn't work. And now these things really do work. Okay. This is basically the same data on that slide, but just recut into our classic bar chart. The reason that I pulled this up is just to highlight how close the top of the chart is, and then to also highlight the fact that all those models at the top of the chart have come out in the last month, basically. So we've seen recent releases from all the frontier labs swapping out those models at the top of the chart. Completing the overview of the AI industry, I want to put this one up here to talk a bit about how we think about a simplified view of the AI stack. So before, I mentioned that we're benchmarking chips, infrastructure, models. This is looking at which companies are playing in each of those parts of the AI stack. So at the top, we've got applications. We can think about ChatGPT. We can think about everything that, as a consumer or business user, you touch as an application at that top layer. Below that, we've got the foundation model layer. There we're thinking about GPT-5, we're thinking about Mistral Large 3, all of the LLMs that sit behind the applications. Below that, we've got the cloud inference layer. So these are the APIs that you hit as a developer to run these models. And below that, we've got the accelerator hardware. Briefly going through them, the couple of things that I would call out that are particularly interesting here. First, you've got different degrees of vertical integration for companies through the industry. We've got a little box there around Google because we see Google as the most vertically integrated company that's playing not just in applications and models, but all the way down to having their own cloud infrastructure and their own accelerators with TPU. And then we see a variety of different strategies across other companies. Okay. From here, we're going to go into a few of the trends that we're tracking that we think are the most important trends in AI in late 2025. First up, pricing. So, AI has gotten cheaper. Simple statement, surprisingly hard to break down into the exact drivers of and understand why that's true. This slide here is our best shot at putting in one place what's happened with pricing over the last 2.5 years. What we're asserting is that for each level of intelligence, there's been a dramatic decline in price. We're looking at a log axis on the y-axis, by the way, and so that's compressing how dramatic this is. For most of these levels of intelligence, we are looking at a 100x decline in cost for that level of intelligence. Although, I did just switch to saying cost, which we'll talk about in a second, because that can have a broader meaning. The easiest line to look at is that light blue one that's got GPT-4 at the start. We can just see that that's declined by 100x and how much it costs to produce tokens that are as intelligent as the original GPT-4. You can also maybe squint and see on this slide here that on the right-hand side, those lines are dropping faster than the lines on the left-hand side were. So what that would mean is that for each new level of intelligence that's being achieved, which we're defining here as these buckets of intelligence index scores, that we're getting the cost decline happening faster, not slower. That makes sense in a world where AI is more competitive than ever. but potentially indicates that once you achieve a new level of intelligence, your ability to price that at a high level is, for a long time, is actually less now than it was even a year or two ago. But we also all, I think, would acknowledge that at the same time as everything I just showed being true, AI is getting more expensive. This slide here is us trying to put all these drivers in one place to explain how both those things can be true at the same time. It is true that GPT-4 level intelligence is 100x cheaper. It is also true that on a single AI query today, it's trivial to spend at least 10 times more than you would have spent on a single GPT-4 query 2 years ago. How do we get to that? On the left-hand side, we've got some of the drivers of things getting cheaper. The biggest one is smaller models and sparsity. The models that we're able to train today that deliver similar intelligence to GPT-4 are a whole lot smaller and a whole lot more sparse. We've also got software efficiency and hardware efficiency. On software efficiency, we're thinking about the techniques in all of the ways that we run inference on these models. And with hardware, we're basically thinking about the new hardware generations. A couple of years ago, we were dealing with NVIDIA Hopper as the latest new exciting thing. Now, obviously, we've got the NVIDIA Blackwell generation, a handful of competitors, and next generations are already coming out right now. On the right-hand side, we've got some of these drivers that take us back up to getting to at least 10x more expensive than a normal GPT-4 query. So, larger models. Our guess is that the biggest frontier models today are actually bigger than the original GPT-4 model that was rumored to be 1.8 trillion parameters. Reasoning models, call this the broad bucket of models using a whole bunch of tokens to do a task. We're going to define this term reasoning models in a minute and look at some of the data on it. And AI agents, call this everything where we're letting models do more than one thing to give us an answer. So instead of just asking a question and having it make up the answer, we're letting these models use tools and do many iterations of work before coming back to us. Classic examples are like the search tool in ChatGPT. It's kind of great that it can go and look at a whole bunch of websites before coming back to me on something. Or at the other end of the spectrum for us software engineers, we've got all of the coding agents that everyone's using and that can now edit multiple files, run terminal commands, and work for a significant amount of time. We've got some illustrative numbers that you can multiply together to get to the differences in cost here, but they can be even bigger in reality because as we make these tools work for longer and longer, they're using more and more tokens and more queries. Okay. This here is what that means for a snapshot of the market today. So you can think about those last couple of slides were over time. This one here is stuff that's available right now today. And as it happens, this is like basically the defaults on our homepage with a few added. And so almost all of these models are current models that you actually might be choosing to do something with. So what the heck are we looking at? We've got intelligence on the y-axis again. So that's just using our artificial analysis intelligence index again to summarize how smart the models are. And on the x-axis, we've got how much it cost us to run all of the evals that we run to get to that intelligence index. We've got a log axis again on the x-axis, and so it might be hard to see from far back, but on the far left, we've got $8 as the smallest one that's written on there, but I can tell you that Mistral Small 3B cost us about $5, I think, for the complete intelligence index run. And then on the far right-hand side, we have $2,000. You can actually spend more than the far right-hand side of this chart, and you can actually spend less than the far left-hand side. But just taking what's on the slide there now, we have nearly 3 orders of magnitude of difference in how much it costs you to get a thing done using today's AI models. That's kind of nuts. That is very different to what you have in most industries where you're picking any kind of product. I try to use car analogies with a lot of our enterprise clients sometimes, but this is like not even the difference between a Prius and a Ferrari. It's many times more than that because we're literally talking about nearly 1,000 times more spend to do something that some users might not even be able to tell the difference between the answers on because those models on the far left can actually get quite a lot done. One of the things that as like a side goal of this talk is to give you a preview of a lot of the stuff that we have on the Artificial Analysis website so that you can understand as developers what you can do with it. This one here is an excellent example of that because this is probably the simplest way to get a realistic sense of how much these different models are going to cost before you go and use something. Okay, reasoning models. As I mentioned before, I want to take a second to define what reasoning models are. We use the term quite liberally to just mean any of these models that think before they answer with a defined reasoning trace, as opposed to starting to write the user answer immediately. A year ago, earlier this year, when I did talks like this, it was super easy to throw up a slide of the reasoning models and the non-reasoning models, show that they use 10x more tokens. We've got this clear definition. We use the little light bulb on all the other charts, like you'll see it on, like on this one here, and on the bar charts and stuff for the reasoning models, easy as. But story is no longer quite that simple. On this one here, we're looking at, again, intelligence index on the y-axis. On the x-axis now, the number of tokens used across all the evals in our intelligence index. And what you'll notice is no longer just two circles. We've got an almost continuous spectrum of models from not using many tokens to using lots of tokens. The way that I think it's best to think about this now is to call it token efficiency as a general concept, and to acknowledge that while there is still a useful differentiation, you actually do want to know what the token efficiency of a model is, because the least token efficient non-reasoning models actually do talk a lot and will reason for quite a while just in their answers to the user. And the most token efficient reasoning models can not use that many tokens and actually be quite efficient. So as a developer, when you're picking a model, it's not just reasoning and non-reasoning. Think about the token efficiency, because that's the number that's going to drive how long the users need to wait and how much it's going to cost you. All right, open weights models. This one here is just the same chart that we looked at before of the current state of our intelligence index, but split into proprietary and open weights models. It's been a kind of crazy year for open weights models in 2025. Overall, we've seen the difference between the maximum intelligence of proprietary models and open weights models stay relatively constant when you zoom out, but that's actually the crazy thing. Like, the crazy thing is that the open weights models have roughly kept up with the proprietary models. Notably, we have a whole bunch of models coming out of China that have become extremely significant. So right now, as we stand here today, we've got Moonshot's Kimi K2 Thinking as the leading open weights model, followed by DeepSeek's V3.2 that came out just on Monday. And then we've got Minimax's M2, OpenAI's GPT-OSS, and then Alibaba's Qwen 3 as the next open weights models. You'll note then that out of those top 5 open weights models that we're tracking today, 4 out of 5 of those come from Chinese labs. That's been roughly the case over the course of this year, and the outlook seems to be that that's going to continue. Why is that? Mostly it appears that there's a very stable incentive for labs who are not competing at the absolute frontier with the OpenAI, Anthropic, Google, and xAIs of the world to release their models open weights so that they can get the benefits of distribution, name recognition much more quickly. Bunch of interesting questions on what that's going to mean for the economics in the future, but for now, it's actually worked out quite well economically for a lot of the companies who have decided to, but has been a pretty brutal race. None of those models existed that I just mentioned existed 6 months ago, and the companies who have been at the top have been changing very, very quickly. This one here is the open weights models again, but just switching it to the over time view. Here's where I want to start to talk a little bit about the European angle on this. I'm based in San Francisco, by the way, and so mostly spend my time with Americans. I'm from New Zealand originally, though. So call it, at least in Europe, there are some quite exciting things happening. We have Magistral Small as the leading open weights model from Europe. That is actually still the case today, despite Mistral Large 3 launching 2 days ago. And the reason for that is that you get quite a lot of benefit in the intelligence evals on account of having done the RL for reasoning. That's pretty important to understand as you think about these models, and is especially important for putting in context Mistral's launch that I do want to talk about in some more detail. It's not entirely fair to compare models where one gets to use more than 10 times the number of tokens that another model gets to use to answer the questions, and even more pertinently, one that's been trained to do that versus hasn't been. There are different use cases there. So, concluding on this slide here, main significant thing to note is just that for most of the last, I think call it over a year now, that line for China has been leading on open weights models. OpenAI's GPT-OSS 120B is a great model and did briefly top this chart, but we're back to the China line being at the top. And if that, like, broadly my expectation is for that trend to continue. And so, like, that is an important thing to be aware of if you're picking models and thinking about where you're going to be getting open weights models from into 2026. Okay, the Mistral models. So, we have Magistral, Meteor 1.2 as Mistral's leading model still, despite them launching Mistral Large 3. This has been a little bit of a controversial topic on Twitter this week, and so that's honestly the main reason that I've put this in with all of them on it like this. Mistral Large 3 losing to Magistral Medium 1.2 should not be a surprise because it is an instruct model, not a reasoning model, and has not yet gone through reinforcement learning to do that reasoning to answer all the questions in the index. And that also means that it is far, far more token efficient than the reasoning models that we're comparing it to on this chart. The reason that I talk about this is because there's been a bit of potential disappointment in where Mistral Large 3 landed, and I want to be clear that this is not a bad story. So compared to all of the models on here that have got those little light bulbs, once we get a reasoning version of Mistral Large 3, I think it's probably reasonable to assume it's going to do better than their previous medium model. It's going to be looking pretty good. The other exciting thing that Mistral launched are the Ministral small models, the 3B, 8B, and 14B. And those ones, token efficiency, as I said, those ones, the Ministrals, are particularly exciting for being small multimodal models that are open weights and permissively licensed. It's actually a pretty small universe of models that are small open weights and can take image input. And so if we look at them zooming in on only those other models that it's fair to compare them to here, actually we see that they're really compelling and quite exciting. We're looking at them here next to the Qwen 3 VLs from Alibaba and Google's Gemma family that honestly I think are the only two important families of small multimodal models. So big fan of those ones. All right, continuing on the European theme, we've recently added scale-away inference endpoints to artificial analysis. I wanted to bring this up in part as an opportunity to just talk about one of the important things that we cover in artificial analysis, which is not just the intelligence of the models, but every inference provider serving APIs for these models, where we're able to cover the speed they're serving, the time to first token, the time to first token under a range of workloads, that's that clustered column there, how all of these evolve over time. And what this means as a developer is that you can go pick the best thing across all the providers that you have as options. Okay. Next thing I'm going to do is talk briefly through a couple of the specific new evals and projects that we've launched at Artificial Analysis. This one here, we launched just over a week ago, and it's called Artificial Analysis Omniscience. We built this to test knowledge and hallucination of these language models. It is not an intelligence test, and so when it's not getting the models to work through problems, it really is just seeing what they know, but they're prompted in a way where we tell them, if you don't know the answer, you shouldn't tell us the answer, or sorry, if you don't know the answer, you should tell us that you don't know the answer instead of guessing. And that means that we think it's quite helpful to take this view here, where we give them points for getting them right and take away points for getting them wrong. The boldest version of this assertion is that hallucination is an incentive problem. It's an incentive problem for the models and for the labs. The way that most AI benchmarking until now has been done is that you get more points for getting more questions right. And so there's an incentive for the models to take a shot at every question. And a lot of the time, that actually is the behavior we want. When I'm trying to get a model to make a change to one of the charts on the website, I would prefer that it takes a shot and I can have a look at what it's done, as opposed to it saying it doesn't think it can do it. But if we're asking a factual question, the desirable behavior for the model is to say, I don't know, unless it's sure that it can get the right answer to the question. So this index here gives us some very interesting results that are different to general intelligence and that we can break out in a couple of cool ways. This is the summary view. We take the points off. And then here we've got hallucination rate and accuracy, the two submetrics that sit behind that index. The hallucination rate metric is the proportion of the time when the model isn't able to get the right answer that it gives us an incorrect answer instead of saying, I don't know. One interesting thing that we see there is that Anthropic's Claude models, despite not actually winning overall, have the lowest hallucination rate. The other thing we see is that broadly the hallucination rates are just extremely high. And this is a hard eval. It's designed to be a hard frontier eval. And so it shouldn't be surprising that the models get a lot of questions wrong. But they are generally pretty bad at being well calibrated on knowing that they don't know the answer. The accuracy number at the bottom there, that's just the simple like normal percentage correct that compares nicely to other evaluation data sets. One interesting fact about this is that factual knowledge tracks quite precisely against total parameter count for LLMs. You do have to add a bit of an efficiency factor, and a lot of progress has been made over the last couple of years, but it's a pretty solid correlation. So there's an interesting bit of analysis that you can do using that omniscience accuracy number to guess how big some of the models are that we don't have disclosure of the size of. And when you do that analysis, it results in it looking like the leading proprietary models today, Gemini 3 Pro and Claude 4.5 Opus, are pretty massive models. All right. The next new thing that we've done I want to talk about is our openness index. This is not an evaluation data set. It's a framework and a way of thinking about how open models are. When I skated through the open weight stuff before, I'm sure everyone understood, but I was obviously just talking about whether or not we can get a copy of the model, right? I didn't explicitly talk about how any of them are licensed, what we're allowed to do with the models and what our obligations are. And I certainly wasn't talking at all about how transparent the creator of the model was about how they built it, their training data, and the methodology and code that went into training that model. But all that other stuff is actually pretty important. So we built this and launched it just this Monday to help the world better understand a broader view of how open these models are, to look not just at are the weights available, but what are the licensing obligations around those weights, what can you do with them, but how the model was made and how that stuff is licensed. A model that gets a perfect score on Openness Index, which Olmo 3 from the Allen Institute for AI comes the closest to getting currently. A model that gets a perfect score would have its weights open, be permissively licensed so that you can do anything with it with like an Apache 2 or other OSI license. It would also have been launched with sufficient disclosure that it is possible to replicate the final checkpoint for that model, to recreate those weights by doing the full training run externally. Okay, I only have 1 more minute. So the last thing that I'm going to finish on is just to take a step away from language models and talk super briefly about image and video models. It has been a wild year for image and video generation. There are upsides and some downsides for our social media feeds of the amount of how well these models are performing. There's a huge range of companies that are doing really exciting stuff outside of language models. This here is a cool way of bringing that together. Basically, in our view, a whole bunch of different modalities for image and video started to work well for the first time in 2025. The most exciting ones that I would keep an eye on are doing image editing with 1 or more input images. There are both kind of LLM and diffusion-based models that are doing really well at that with Google's Nano Banana Pro and some other solutions. And video generation, especially image to video, is working really, really well. We have human preference arenas where users vote and we get to construct leaderboards for how all of that stuff is performing. I would highly recommend checking some of it out. Thank you very much. Been great to talk all this through, and I will be around later. Thanks.